Okay, good morning. So, welcome back to the lecture Virtual Prototyping of Embedded Systems. And last time I gave you a quick motivation and introduction to the topic. So, why actually do we need that? And now our next steps would be that we talk about system models. So, how can we model an embedded system by use of, let's say, mathematical tools. And then in the second step, we will start to model actually by using the language System C. Yeah. Okay, so then let's start first with the question, actually, what is a model anyway? And I want to distinguish system and model. So a system is a combination of components that act together to perform a function not possible with any of the individual parts. So it's composed of many other parts, and you have usually inputs to the system, and then you have also outputs. Yeah? So you can also, you put something in, and then you can observe some reaction. And then we have also the architecture, and the architecture describes how the system has to be implemented. So if we talk about architecture, then we mean basically a blueprint how to build the system. Whereas when we have the model, this is usually a formal description of the system. And this part is even more important now. In a model, you can only cover selected information. So the model usually cannot represent the complete reality. It always abstracts something. Yeah, so here maybe some additional inputs are missing and some outputs are not really modeled. And also maybe inside something is more abstract. Yeah, and this model describes the behavior of the system, and this is very important. It cannot cover all the aspects of the real system. I want to give you an example, small experiment. Let's assume we have a house here, and there we have 3 light bulbs, and these are controlled by 3 switches. Yeah? So if you know the example, please don't say anything. It's for me about the experience that you have now. And your task is basically to figure out which switch belongs to which light bulb. Yeah? And you cannot see it. So from downstairs, you cannot see the light bulbs. And your task is to figure out the correspondence, but you are only allowed to walk up and check only once. Yeah, so this is basically a model that I give to you now of a specific system, this house. And now you should figure that out. So think a little bit about it. How could you, is it even possible if you are only allowed to go up once? Any ideas? Yeah?
I don't know, I'm very sure, but I would say it's not possible to go to with only going on once, because there's always 2 bulbs and 2 switches at the same state, and you cannot distinguish them.
Yeah. Yes, it's correct. With the information that I gave you about the system, so I made a model up in your mind, right? I think it's not possible, but in reality it is possible. So how could you solve that? Yeah.
By flipping 2 light switches and taking the one you can maybe see from the stairs to like figure out which the dot switch is.
No. So I did not tell you an important aspect. So these are really old light bulbs, not LED lights, old light bulbs. Yeah.
With temperature maybe?
Exactly. So can you explain it maybe already?
Yes, turn on 2, then turn turn one off and go upstairs, then one is lightning, you know what it is. One is warm, that's the upper, and the cold is the last.
Yeah, so something like that. Yeah, so you switch on one and then you wait for 10 minutes. And then one of those will be really hot, but then you switch it off and you turn on another one and then you have the mapping. Yeah? So the important thing is here, I gave you a model, but I missed the aspect of temperature. Yeah? So if I would say directly, okay, and also temperature plays a role, then you would figure it out directly. Yeah? So therefore, models enable thinking, so we can think about a system and we can discuss about it when we use such a model. But also models hamper our perception. That's also important. So it might be that you miss important aspects because this is not modeled in your model. Yeah? Okay, I also give you there an example. What we perceive and how we interpret that what we see or observe depends on the frame through which we view the world around us, right? So if you just look on these frames here, you would say, okay, when I look, can show it. When I look through this one, I would see a city. And if I look through this one, then I would see a beautiful landscape somewhere out in nowhere. And here I would say, okay, it's raining. So I make an extrapolation basically. So I just see the frames, but then I conclude what's around. And the reality might be different. So this might be just a view to Central Park in New York City. Yeah? And this is not raining, this is just water coming out of this. And here you see the park and there you see the buildings. Yeah? So that's important. So if you model, you have to make sure that you always use the right level of abstraction that is required for the information that you want to get out of these models. Okay, let's talk a little bit about time and state. I think you know that because you studied computer science in the past. When we talk about states, we have usually discrete states. So we can model this, for example, with a state machine, and the states are countable. Yeah? So it's a countable number, basically. But we also have systems that have a continuous state. So I can model here an electrical circuit and can describe it with differential equations. Yeah? And then the states are not countable anymore, they are real numbers. Yeah? So in this case, there's a capacitor that can be charged or discharged to an arbitrary voltage, basically. And on the other hand, we have also time. So we could have discrete time, where we have countable number of timestamps. And this could be combined also with discrete states. Then you would see something like this. So in your system is then at point 0 in this state, and point 1 it's in that state, and so on and so forth. Yeah? But you could also mix discrete time with continuous states. So you see then you don't have the states x1 to x4 here. It's a continuous space here. And then, of course, you can have continuous time. And also the combination. So you have here a finite amount of states, and then the time is continuous, but you could also have here continuous state space and continuous time, and then you can describe functions like charging a capacitor. Yeah? I think that's also pretty obvious. The problem is if we now do simulations and we want to build a model that simulates time, we always have the difficult thing of how do we do it, because our computer is a discrete system. Yeah? So our CPU, where the simulation runs, has a clock, and it runs basically in discrete steps. So we will talk about that. How can we simulate also continuous time with discrete machine, basically. When we simulate time, we have also some concepts that we have to look at. So this is the discrete time simulation, where we always execute simulation with fixed time steps. Yeah, so we say, okay, maybe this is 10 nanoseconds or whatever, and then we simulate in these steps, basically. Input ports of the model are constant during a time step, and the output ports are updated at the end of a time step. And this is a trade-off between speed and accuracy, and this we will talk about this a lot. So we always trade off speed versus accuracy. So if you want to have a fast simulation, then usually the accuracy goes down, and if we want to have a very accurate simulation, then the speed will go down. Yeah, and then we have discrete event simulation, and this is also a very different concept because the events that are simulated may occur at any time. So it's not that we have a fixed amount of time steps, always with the same distance. So the distance here between events can also vary. And we will talk about this in the lecture a lot. So the events are sorted in a queue according to their expiration time. And in discrete event simulation, we use the concept of a two-dimensional time, which is also often called super dense time or delta delay. You see it here, so we will talk about this. And with that, you can even simulate parallel systems, so systems where a lot of things are happening concurrently. Yeah, the cool thing is you can always model a discrete time simulation by using discrete event simulation. So that's kind of backward compatible, because then you schedule the events to fixed time events. Yeah? So you can basically mimic discrete time simulation with discrete event simulation. Nevertheless, there is always a little bit an overhead because you have here the sorting queue and so on and so forth. So if you want to model directly only with discrete time, it's maybe worth to basically use a simulation kernel that just supports this, because it will simulate faster. But also we will talk about that, the difference between wall clock time and simulated time. Yeah, and then we have continuous time simulation. Also we will talk about that. So we want to approximate the continuous behavior of physics usually, and this leads always to differential equations. And usually we use discrete timestamps, and with the width of the timestamp we can basically steer the accuracy. And how does such a solver work? So usually we simulate a time step, and if we see, okay, the error is too big, then we roll back and then we simulate it again until we converge to a fixed value. We will also talk about this. But you get already the idea. There are basically three concepts how we simulate time in such a simulation. Yeah, so we have continuous time models. We talked about that. Usually we have then numerical equation solvers, and languages that support that are Simulink, Verilog or VHDL, AMS, SPICE, and so on and so forth. Discrete time models, by the way, also System C supports that already in the meanwhile. Discrete time models, we have usually VHDL, Verilog, System C, you can do it with that. Synchronous models, that's also interesting, we will talk about this also a bit, where time is also represented by a discrete set. There are also languages like Lustro or something like that. And then there are untimed models, where we have no notion of time. because we don't need it, it's not interesting. So the ordering of the events is more important than the actual timing. And there a specific untimed model would be a Kahn process network. Who has heard about Kahn process networks before? Okay, cool. Then I will show it to you probably already today. Yeah, so there are many models of simulation and computation. Some of them you know already. Yeah, so finite state machine you all know, right? So who has heard about Petri nets already? 1, 2, 3. In which context? Which lecture was it? Okay, interesting. Mm-hmm. Okay. Yeah, makes sense. So I especially like them a lot because with them you can express also parallel behavior very well. This is the Kahn process network. So discrete event simulation, you probably know already when you attended Rechenanlagen, because there I explained the simulation kernel of VHDL or Verilog. Yeah, so we will go through these different models of computations, and we will talk about, also are they deterministic, are they able to model concurrency, and do they model time or not. So we will go through them now in the lecture. Yeah, so I said already many times that System C will be our tool language. And in System C, you can basically model everything. So you can do discrete event simulation, similar to Verilog and VHDL. You can model state machines. You can also do some network modeling, queuing models or whatever. And this is very special in System C. So I think no other languages have that. This is transaction level modeling, which is very powerful. Continuous time with System C AMS, you can also model continuous time. You can model Kahn process networks. I think that's even part of an exercise. You can model data flow systems. That's also interesting. We will talk about that as well. Dynamic multi-rate data flow, communication of sequential processes. So you can even model software with System C, which is also sometimes helpful. Yeah, you can model Petri nets. That will be also part of the exercise, and many more. So with System C, you can basically model all these models of computations if you want. Okay. I said already, a model is usually an abstract representation, and we try to make it always in a way that it's implementation independent, but sometimes it doesn't work, so we put some more information in it. The cool thing about the system models is that we can move up the level of abstraction, so it gets much easier to model something, especially in System C when we have TLM. It's much easier to model something in TLM compared to, for example, VHDL or Verilog in a cycle-accurate way. Yeah? And this also helps us already to validate much earlier. The cool thing about a system model is also that we usually have some kind of formal representation. So we can also sometimes prove something. This is also pretty helpful. Okay, what this lecture will not be about, and therefore I put the excursion on it, there are also some high-level languages to model something. So you know UML for sure, but have you heard about SysML also? Okay, so in embedded systems, this is basically let's say an extension to UML. So some parts of UML are also included in SysML. And this is driven by object orientation a lot. And there we use basically SysML to model systems mainly with pen and paper, I would call it like this. Not so much with simulation, but sometimes it can also be combined with simulation. Yeah, and this is a lot of industry-driven, and it also includes hardware, software, mechanics, human services, and whatever. So to give you just a brief idea, so as I said, the lecture is not about this, so you could make an own lecture on SysML for modeling of embedded systems. But some of the things you will recognize here. So you can model structure. This is a classical UML diagram, where you say, okay, this is composed of that and blah, blah, blah. You can model behavior, and there are different things. So there is a so-called activity chart that borrowed basically the semantics from Petri-nets, so it's pretty similar. Yeah, you have also the possibility to model state machines, and there is also an interaction scheme. Actually, I don't know exactly what that is, but state machines and activity is clear. Yeah, and then you can model more physical things with parametrics. There you can put your differential equations in this kind of Simulink fashion. So you can describe the system then by differential equations. And third, here there is also a requirement package. So you can also specify requirements. And the cool thing is in these typical tools that you have, drawing tools, which are also sometimes smart, like Enterprise Architect, for example, you can also link then these different objects. So you could have here a requirement that is then linked to a structure, and the behavior of, this anti-lock controller is described then with such a structure or with a logical structure behavior here. Yeah, and then you have the traceability between all these model artifacts. But usually this is not simulation. So some people try then to bring this then also to a solver and solve differential equations. But it's more the focus on the documentation, I would say. Yeah, and this was a little bit the history, but I will skip on that now. Okay. So state machines. I think you know that, right? So I don't have to talk so much about that. You can write it down mathematically. So you have a finite state machine is described by this 6 tuple here. So you have states, inputs, outputs, and then a bunch of functions here that describe that. Yeah? And then this is the typical state machine. You have maybe an initial state here. Sometimes you have an arrow that points in it, but here they use, for example, a second circle around it. And then something happens, start is issued, and then you go from that state in that state, and then if a 0 happens, you stay in that state, or if the end command comes, then you go out of it. Yeah? So this is typical state machine. So to give you an example, I use now a system that I work with a lot, which is the memory system, and in particular DRAMs. And I just want to use that as an example to show you the problems and the limits of state machines. Yeah? Okay, so how is such a simple DRAM built? You have a single memory bank, for example, and it's a very abstract model. So the experts know that this is not true. It's an abstract model. But as I said, I use it just for an example. because in reality there is no row buffer, but let's now think about it as it would exist. So this is our external memory, and the CPU will now do some requests. But if the CPU is not requesting any data from the memory, then we are in the idle state. Yeah? Okay, fair. If we want to read data from this memory array, we have to send a so-called activate command. And this activate command will basically copy a whole row here. So these are all the cells. Yeah? So I don't know, we have there maybe 16,000 entries in that direction, and then we have 16 kilobit in that direction, for example. So, and now we send an activate command, and with this activate command we want to specify one specific row in this matrix that we want to read. So if we issue the activate command, then the data is basically copied to this row buffer. Yeah? And this is what we see here. So we are in the idle state, we send an activate command, and then we are in the active state. Yeah? And now we can do reads and writes. Yeah? So now we can do write operations to this data, we can do read operations, but then the data is not yet stored in the final destination row, it's just in this row buffer. And therefore we have the precharge command, and if you issue this precharge command, the data is copied basically back. And as I said, disclaimer, this is not really true. In reality, it's a little bit more complex, but for now, it's enough to understand the DRAM commands that the memory controller of the CPU has to send. Yeah, so when we send precharge, we go back to the idle state, and the data is then stored safely again in these rows. Okay, cool. Very simple state machine, right? So, but the reality is also not the case that we have only one of these memory banks. Today we have 8 to 16 of these memory banks, right? So let's go one step further. When we have now a 2-bank system, we have more states now. So it could be that this bank is active, or here this state, this bank is active, or this state, both banks are active. So both banks have one activated row. Yeah, and you see already the state machine gets a little bit more complicated. So, okay, but this is not yet the reality. So our banks are independent. We can do parallel access. Yeah? So if we go for 4 banks, then the state machine looks already like this. Yeah? And then 8 banks, which is the first actual DRAM that you could buy, the state machine looks like this. Yeah? So this is what we call a state explosion. And in this example, I think you really see that exploding. Yeah? So you can also calculate it. So this is the number of banks, B. Then you will have basically 2 to the power of B states, approximately. Yeah? And this is also, I calculated that once. This is the number of edges that you have in between. This is also interesting. So that kind of explodes, it's exponential, yeah, so it's 2 to the power of B. And that's the problem that we have with state machines. So for complex systems, they tend to explode. Especially then when it's parallel, yeah, so actually, when you model parallel systems, then the state machines usually explode. Yeah? And there, P-tree-nets are much better, because they are made to express concurrency and parallelism, yeah? So that you can work with all these different rows or different banks in parallel. So let's talk about them. So yeah, P-tree-nets are models for concurrent and also asynchronous systems. So you can also make them synchronous easily, but the concurrent thing is the most interesting part. Okay, so in Petri nets, we also have states, but we call them places. And if a state is basically on or off, this is determined by so-called tokens. But between the places, we also have so-called transitions. And the transition usually represents then an event. Yeah? So this is the transition. And then we have arcs. So this is also interesting. This is also directed. And these arcs connect places and transitions. And it's always in that way that a place connects to a transition and a transition then to a place. It's never the case that two places are connected or two transitions are connected. So you always have from place to transition and from transition to place, but never from place to place or transition to transition. And they can have a weight also. That's also very powerful. There you have the weight 1. And if an arc doesn't have any annotation, then it's always weight 1 standard. But here you could have also a weight of 2. Yeah? And this is related now to the tokens. So tokens, you can think like a coin that you put there and you can move that coin. And it's always the case when such a transition now fires that it consumes tokens on the input places and basically eats them. And then it produces new tokens depending on the number that is there on the output arc. So what is now the firing rule? So we call a transition enabled if and only if the number of tokens is larger or equal to the weight that is there. So therefore this transition is now green because it has one token here, yeah, that's true, and here it has 2 tokens, and therefore it's enabled. That doesn't mean that it fires, so we need an additional event to fire it. It just means that enabled just means that the transition may fire. It doesn't automatically fire. And then when we fire it, we remove the amount of tokens according to the weight, and they are consumed basically, and then we generate 2 new tokens. And then the transition may be disabled. So let's do that. So let's fire T1. So the tokens go there. And then 2 new tokens are generated. And now you see it's now disabled because there are not any more tokens available. So we are not allowed to fire because we would need 2 tokens here to be enabled again. Yeah? So that's it, basically. So you can also describe that in a very mathematical fashion, but I will skip that, but it's just there for completeness if you want to see it a little bit more theoretically. So this was the basic idea, basic Petri nets, but they are not yet Turing complete, and you can reach that by 2 extensions, so-called reset arcs and the inhibitor arcs. So let's first talk about reset arcs. So what is the idea of that? Basically, you see it here. So if this transition fires, and then it will remove the tokens from the place that is connected to this transition with the reset arc. So I just simulate that. So here we have the weight of 1. So if I fire now T1, then this token is consumed and goes over there. And because of this firing, we will also remove these tokens, and then also this here will be disabled. So let's do it. So let's consume 1 token. Then they get deleted, and then all these tokens basically are vanished. And this transition was fired, but now there are no tokens anymore on the input here, and this cannot fire anymore. This could still fire again because there is still one token remaining. Okay, so then the other thing, inhibitor arcs, and there's the idea that they inhibit the firing. So it's the other way around. So this is the arc that shows that. That means that if a token is on this place, this transition is not allowed to fire, even though it would have enough tokens on the input. Yeah, so if we execute T2, we move a token to P4. So now this is disabled because it doesn't have anything on the inputs anymore. But now also this is disabled or inhibited. The execution of or firing is inhibited because we have a token on P4. And even though there is still an input token, it may not fire again. Yeah, so we can use that to block some things. And this is also required if we want to model again our memory bank example. So how does the P3net for this simple one bank case looks like? It's just like this. We have a state that is called idle. And we have just one token there. Yeah? So if we send now an activate command, we want to activate a row. So would that even work? Yes, because there is a token on the input. And we could now send an activate command. So let's do that. Yeah, so we execute the activate command, then the data is copied to the row buffer, and then we are in the active state. Yeah. And now we can execute again reads and writes, which are also now here these commands, yeah, that are transitions. So we execute a read, we execute a write, and then we want to close the row again, and then we send a precharge command, and then we are back to the idle state, and now you see also those cannot fire anymore because we are missing the token on the active state. Okay, now you would say, okay, that's much more complicated than the two-state machine that we had before. That's true for the single bank, but now that can scale. So if we want to have a two-bank system, we just copy the P3net, basically, and just connect it then to the idle state, and we also increase the number of tokens. Yeah? So we have 2 tokens now. Okay, so let's look at this example. We activate a row in this bank. Yeah? So that is active, and then we activate another row in this bank. Oh, that won't work physically. You can always activate only one row, so you cannot activate 2 rows. So if you would do that, maybe you get a logical OR of these of the data that is inside. So you can maybe compute with it, but it's not intended usually to compute with the memory you want to store something. So this is a problem. So we can activate 2 banks at the same time, 2 rows in one bank at the same time. That should not work. How could we prevent this? Yes? Exactly. So from where to where?
From active to act.
Yeah. So from active to act, we put the inhibitor arc. So let's go back. So we put there the inhibitor arc. And if we now activate the first bank, so the token travels to the active state, then it's now blocked and we cannot activate it again. Yeah? Very simple solution. And now we have a working model that scales. Yeah? So we did not need basically the inhibitor arc in the simple one because there is no parallelism yet. But now we add this here, and then now it scales. So the 4-bank system looks like this, yeah, and then the 8-bank system looks like this. So of course you need then a lot of more tokens, but it scales better. So not exponentially, it scales linear. Yeah, so number of banks is again B. The number of states is b plus 1 because we have the idle state. In some 3-4 years ago, we even showed that you don't even need the idle state, but for didactical reasons, I keep it here. So you have basically b plus 1. The number of transitions is then 4 times b, and the number of tokens is b, and the number of edges is 9 times b. So everything scales now linear, and it's much easier to understand. So, and this is not just a toy example, so we model real DRAM systems with this approach. And we wrote already a lot of papers, and you can even try that interactively. So maybe I can also quickly show you that. Let's see. Yeah, so this is an artificial two-bank system, but it has all the usual DRAM commands there. And you can now play around with that. So you can just click on the transitions and you play DRAM controller basically. So you send an activate command, and then you can send a read command, and then you stay in that state. And then if you send a pre-charge command, you go back. But you could also go to self-refresh. Then the DRAM is in a power saving mode, and you cannot do anything beside of waking up again. So this is the self-refresh exit. Yeah. And you can model that. And of course, this is just a demonstration. There's also the possibility to enable timing. So there's your clock beat, and then you can now send an activate command, and then you have timed inhibitors. So this is something that we have invented, that you inhibit then other commands for a specific time. And with that, we model the complete memory protocol. Yeah? So and then if you waited enough, you can also do something, and then you can already in the meanwhile do something else here. And now you are not allowed to do anything until maybe here again, in this cycle. So this helps a lot to model basically this very complex DRAM protocol. Yeah? And also with timings enabled, then it doesn't scale linearly anymore. Then it's again an exponential scaling, even with P3nets. But it's very useful because we do a bunch of things with that. So we generate the source code of a simulator. So P3nets are the mathematical basis, and from that we can then generate also a functional simulator. We use that also to make formal verification of DRAM controllers and DRAM, because we can then generate system Verilog assertions, for example. So there is still a lot of research, and in the meanwhile we model these P3nets in Python. So we have a Python DSL to model all of this. Yeah, so that's the quick introduction to P3nets. And as I said before, in SysML, they basically have copied this. So there also a token can travel through the system. It's pretty similar. Yeah? So it's inspired basically by the P3nets. So if you see something like this, then just think on that. Okay, but UML and SysML, they also introduced something to make state machines more usable. This is what they call hierarchical state machines. And the idea is the following, or the basic idea. You have now a single bank. And for this single small system bank, you have a state machine that we maybe call bank machine. And then you put there the state machine that we had before. And here you put a so-called history node. And this is the important concept that shows that it matters that you save the state in which you are when you leave this subsystem. Yeah. So the history node is used to remember the state in case the supernode is left. So this is what we call then a supernode. And if the supernode is entered again, then the state machine continues in the last active state. So we remember this. And then if you model a two-bank system, it would look like this. So we have here the overall state machine. So when I would talk to bank 0, then I go into this state. If I want to bank 1, then I go to that state. And these states are then hierarchically composed of this smaller state machine, and there we have the history node, where we remember, is this bank now active or is it not active? Yeah, and then that scales, so you can then build basically the 8-bank system like this, also even with state machines, but yeah, you have this history node in place. And also here, if we scale that, we would get a lot of edges, and you can simplify that in this language basically to show, okay, you come from the boundary, you go to bank 4, you do something, and then you go back to the boundary, and then you go to the next bank. Okay, but yeah, you could model the DRAM system also like this, but I prefer the Petri-net approach. Okay, what else? We have time then until 10, right? Yeah. So CAN process networks. Totally different, but also very useful. There's again the mathematical definition, and maybe I dive a little bit into that. Because now it's the first time where we learn something about processes. And this is very, very helpful to understand also later on System C in the discrete event model. Okay, so CAN process networks are deterministic model for distributed systems. A KPN is a directed graph where nodes represent processes. And processes is basically where you put behavior. So also things like if-else statements you are allowed to do there. But the important thing is that these processes must be deterministic. That's important, otherwise the whole KPN thing is not deterministic. And these processes are connected with arcs, and these arcs are not just like connections like we saw in the Petri-net, they are actually queues. So each arc represents an infinite FIFO connecting these processes. And this is also important. These FIFOs are infinitely large. Yeah? If they are not, then things get more complicated, but even then it's solvable. But in the original CAN process network, we assume that they have no limits, basically. That also means that the write to such a queue is non-blocking, because if we have infinite space in such a queue, we can always write something into it. So it's not blocked. Whereas if the queue would be, has some finite number of entries, maybe 5 or whatever, and then you try to write the 6th element into that queue, it would not work. So the queue would block you. Yeah? So that means that if we say that the FIFOs are infinitely large, that automatically implicit says that the writes are non-blocking. Yeah? Nevertheless, the reads they are blocking. So a process will stop to execute here if there is nothing on the input queue, if it waits there. Yeah? So therefore we have blocking read operations. So if the input queue is empty. Okay. So some facts about the KPN. So they are distributed and also concurrent. So that's also very powerful. So they are also deterministic. That means that for the same input history, they must always produce the same output. And because the processes must be deterministic, also they are not allowed to share variables and information. So all the information that flows through the system is only allowed to go through these queues. Yeah, what's there? Because of the FIFO character. Okay, yeah, this is, it's deterministic because of these FIFOs. We will see that in an example. And what is also very important is that processes cannot peek into FIFO. So they just wait for it and then they consume it. They are not allowed to look, oh, is there something in the FIFO? Oh, this is not the case, then I do something else. Yeah? So that is not allowed. And yeah, it's really a beautiful thing that you will see in the example, that actually really it doesn't matter in which order you execute the processes. At the end, you will always get the same result. And this makes it really powerful to model such a concurrent system also with a serial simulator, basically. And we will talk about that also a lot. Yeah, they are also like the P-tree nets with reset and inhibitor arcs. They are Turing equivalent. So you also have here the same thing like halting problems. So you cannot say if such a current process network ever stops. And yeah, as I said, control flow is always in a node. So the control flow is done in the processes, basically. The wrong picture. So here we have the control flow inside. Yeah, so here we use, just as a side note, here we use a state machine to model the behavior of the current process network. Yeah, and we can have also deadlocks that may occur if all processes are in the wait state, but we can handle that, that's easy. Okay, so let's start with the, I think, original example that Kahn proposed back then, and I use here a pseudocode, basically. So in the original paper, it was kind of, I don't know, ADA code or whatever, and I translated it in something that we can read today, which is kind of a C++, Java, whatever code. Yeah? Okay, so this is the Kahn process network of the original publication, and what's the goal of that? It's actually makes not much sense, but it computes the string 01010101 until eternity. Yeah? That's the idea. But with that basic system, you can show already a lot of things. Okay, so let's try to understand that a bit. So processes are described basically like functions or methods. Yeah? But as I said already, they usually are atomic, but they can interrupt it with the so-called wait statement here. And if we do a wait, that means we want to consume something from an input queue. So let's look on the process F here. This is defined here, and there you see it has an input from type integer, which we call u, and then we have another input which we call v, and then we have an output which we call w. So this is just a description of this process, and when we write this, we do not know yet how it is connected. So the connection happens here. So here you see we define some channels like X, Y, Z, T1 and T2. And then we assign these processes these channels. So for example, there internally we call this U, and this U is actually Y. Yeah, because there's Y, and we connect Y with F, and this is the place where it's U. And up there, this is V, yeah, the second parameter. This is basically then the Z or Z here. Yeah. And then we have the output that we call that we call x. And this is connected here. There's another output, but this output here actually is not going to a queue anymore. This is just a print statement that we have here. Okay, so let's try to understand this now a bit. So here we have some initial helping variables, I, and then we have a Boolean b. Okay, and then we have an infinite while loop. And you see that we have that everywhere. So that could also be a for loop, it doesn't matter. But it's important that we have this concept here of an infinite loop. Yeah, so this runs forever. Okay, so then we execute maybe this process first for the first time, and then we enter into this while loop, and then we have this ternary operator. Are you aware of that? How it works? Who could explain it? So you know this question mark colon operator, right?
It's an inline if.
Yeah, it's an inline if-else thing, right? So if b is true, then we will call the wait function. If it false, then we will call that function, and the return value will be stored in I. Yeah? So that's a short writing for a longer if statement, and it's used in C and many other languages as well. Even Python has this, but with a different syntax, right? Okay, so we have an if else. So depending on b, and b in the beginning it's true, right? So that means we will take the first one. So that means wait u, and u is y. So that means, okay, we will wait here in f until we have at least one element in that queue, and if we have it, then we unblock and we continue the execution, and then we consume basically this element, and the data of the element is stored in I, and then we print that. So that's what we see here. Okay, that's the consuming, but we can also send something. So we will send then I, so that what we actually got, we forward that to x, which is w, and w we said is x. So we write that out here again. And then we invert our internal state, which is b. So we invert that. B is not b, so from true we go to false. And that means in the next execution we wait then on something that comes from there. Yeah? So, and it toggles all the time. So we consume here, in the next cycle there, here, there, all the time we toggle. Yeah? Okay, then let's look at maybe also G. What is G doing? It's very similar. So again, an infinite loop. And then here we just wait for one input, which is u, and u for G is x. So this is here. So we consume always that was what is there. And then if our internal state is true, then we send it out to v, and v is t1. So if it's true, we send it down there, and if it's false, we send it up there. Also toggling all the time, because we invert here the b again. Yeah. Okay, and then we have the process h, and this is interesting because we have it two times. So we have it there, and they do the same thing. So why do we need them? Yeah, these are just there to kick off basically the whole thing, because for them we will give them initial values that we send out, and then we also enter to a loop, and then we just forward. Yeah? So we consume something and send it out again. But this is important to get a kickoff here. Basically, we use these processes to get things started, and this is basically here with this initial part before we end up in the infinite loop here. Yeah? Okay, and if you start the system like this, so one H gets a 0, the other H gets a 1. Yeah, so initial here, and then they will produce something, and then obviously you see already that we start to basically kick off this process of producing 0, 1, 0, 1, 0, 1, 0, 1. Yeah. Okay, so again, summary. So F alternately copies U and V to W and printing each. This is doing basically the same but without any printing. And here we emit an initial token and we copy always the input to the output. Okay, so and what we said now about determinism is that this output here on F, so this printf, will be deterministic independent of how we schedule the execution of these processes. And that's the important thing. So this output will always be deterministic. Yeah, so let's understand that. And this is also from a very interesting paper that describes the original paper again in a more, in an easier way, let's say. We use the same system as here, but here you see it's a little bit, looks a little bit different. But at the end it's the same thing. So we have our F here, we have our H here, and there, and our G there. Yeah? And this is what you see here. So, and in the beginning we have now a choice. What do we do basically first? So if these initial H states, they will emit their tokens. So I think here a 0 and there a 1, or vice versa. I have to check it now carefully, but you get the idea. We have then the choice who can execute next. And actually there is only one possibility, because that could be just basically F that can execute. Okay, so then if we execute F, we have after that, so you see here, this is the 1 coming from the top and the 0 coming from the bottom. And then we execute F, so we consume the 0 and put that in the middle queue. Yeah? But now we have several things. So we can execute G here to consume the 0, or we can execute again F. Yeah? And now you would say, okay, if we do that, it might be that we get a different output, that it's maybe not deterministic. But this is proven in this original Kahn paper that it doesn't matter, actually. So I don't want to prove it here, so if you want, you can do it by yourself again. But I want just to show you that it really is like this. So now we have a choice, so we can execute F and consume the 1 from the top, or we can execute G. So, and now let's do both passes in parallel. So if we execute now F1, the output, of course, here it was 0, then the output was 1 here. Then we go in a state where we have 0, 1 in the middle queue. And then we can only execute G again. Yeah? But if we execute G, then the token travels to down there again, to the H node, and the 1 is still there. So we can then execute H, but we could also execute F, and then the output will also be F, will also be 1. Yeah? And the scheduler of this simulation, or of this simulator, will decide that. And usually it's a random fashion, and it doesn't matter, because at the end the output will be the same. Yeah, so if we then execute F1, we go that way, so the output is then also 1. Yeah, first output 0, next output 1. It's the same like here, output 0, output 1, works. But here we have another choice, we can execute H. Yeah, so then we go to that state, and then there's only one thing that we can do. Also there we execute then F, and also the output will be 1. Yeah? So if we travel again here, output 0, then we go here, no output, then we go there, no output, but here we have now an output and it's again 1, 0, 1. So works. Yeah? So independent of the choice of the scheduler, the output of the process is always the same. And Kahn proved that in the paper, that this is always the case. And that's now interesting. You can now calculate also the FIFO sizes. And this depends on the scheduler. So if you define a specific schedule for all of these processes, you can optimize basically the amount of memory that you need for the queues. Yeah, that's also an important takeaway. Because in reality, we don't have infinite queues. So this works, of course, always with infinite queues, but in reality, we are always bounded. We have not unlimited amount of memory. Yeah, so you see the second output in any way we go is always 1. And with that, you can model now a lot of different systems. So one example is here. This is an assembly line for a car, for example. So you have producers, so you will produce the body of a car, the front left door, front right door, rear left, rear right door. And then you have a process that takes all these parts, assembles it, and then you get a car out, and this car you then put into the paint process, and then you paint the car. So how would that look like in the pseudocode? So we have an assemble function, for example, that is again in an infinite loop. But I just want to show you here that we can also have now control flow in that. So we consume a body, or so here I put now read, but in the previous example it was wait, doesn't matter. So we have a blocking read here, and if we have a body, then we continue. But then we see, oh, is this body belonging to a cabrio or is it an usual car? And if we have a cabrio, then we have only maybe 2 doors, and then we just produce now, we build a car based from the body and then from 2 doors, and then we are writing the result. But if it's a normal car, then we would have 4 doors, and then we consume 4 doors, and then we create the car and write it out. Yeah, so that's the idea. We can put control flow into that, also depending of our data. Yeah. But even then, it's still deterministic. It only gets non-deterministic if we would draw here a random number from a true random number source or something like that and make it non-deterministic. And then the whole determinism also breaks. Yeah, so KPN usually has an infinite FIFO, but in reality, as said, we have a bounded size. And if we use bounded FIFOs, we can mathematically derive from the schedule the sizes. However, this is again not possible for all KPNs, as you have already probably thought of. And we have the same thing as for every Turing machine, we have the halting problem. So for some it works, but sometimes it doesn't work. Yeah? And we could have artificial deadlocks, and an artificial deadlock is that what happens when such a FIFO is full and we want to write to a full FIFO. Yeah? And there's an algorithm to basically also during runtime solve these issues. And this is actually quite clever. So we set all FIFOs in the beginning to 1. And if such an artificial deadlock happens, then we just increase the size of the FIFO. If we do that in software, it works. So we allocate a little bit more memory and then it will work. We can handle all of this in a data structure. And if that happens again, then we just do that again and we increase the FIFO, and then after some time the system basically will adopt to the right FIFO sizes. Yeah. That's the idea of Park's algorithm. Yeah, and on top of KPN, there is also something which is called synchronous data flow, which was published by Edward Lee in 1987. And this is basically a restriction of Khan process networks to avoid these buffer overflows. And how does it work? Yeah, the idea is that the nodes produce and consume a fixed number of data items per firing. And then this allows us to make static offline scheduling. And yeah, we can then compute the relative execution rates by solving a system of linear equations. We will also look into this when we talk about System C AMS. And then we can determine a periodic schedule by simulating the system for a single round. And then the schedule can be executed repeatedly without accumulating tokens in buffers. Yes?
I have a question to the Park algorithm.
Mm-hmm.
Is it guaranteed that it finds a valid solution? It sounds a little bit like the holding problem.
Yes, at the end, this still is there. Yeah? But usually for the systems that we model, it works, that we not run into this problem. But in general, I think yes. Yeah. It could be that then at some time then you are out of memory because it cannot allocate anything anymore, and then you will run into this problem. Yeah. So where are KPNs used actually? It's kind of interesting. So compilers are using that. So there are actually two products that are there with the goal to transform legacy code, which is written in a serial fashion, automatically into a parallel code. Yeah, so that you can execute it on a multi-core system or GPU or FPGA. And there, the compiler guys, they basically try to figure out what are the basic blocks of such a program, and then they put them in processes and do this communication. And as you can see here, things can happen in parallel. And this is also very important. So if you build that in a real system and you don't want to simulate it, then this will happen in parallel. If you build that in hardware, for example. Yeah? But here, of course, it's not really happening in parallel because we have a sequential simulator or sequential scheduler that decides, okay, now this process and this process. But actually, it happens already concurrently. And this is also what we will see in the discrete event simulation when we talk about super dense time. Yeah, and this is what they exploit basically, that things can happen in Khan process networks in parallel. So they take the legacy C code or whatever, and then they transform that into a Khan process network. And then they can now assign these processes to different cores, and then they can run it in parallel. So that's the idea of automatically distributing serial code to a multi-core system. Yeah? So it's not useless to know this system model. So there was the Silexica compiler and also Compan in the past. I don't know if so Silexica was acquired by Xilinx, and then Xilinx got acquired by AMD. So I don't know if this technology is even around nowadays. So, but they use it also then for FPGA, so for high-level synthesis, that you can convert C code directly to Verilog. Okay. So the question is, if I probably don't have enough time to talk fully about this now, but I ask again, who has attended my Rechenanlagen lecture in the past? Okay, then it's worth to explain this in full detail again. This is another concept, which is called discrete event simulation or discrete event models. And we have the same concept of processes again. That's important. So this is, therefore I show the Kahn process networks first, that you are already aware what is a process. So a process describes functional behavior, and processes are here now not triggered by queues or blocking, so they are triggered by a so-called event. Something happened, and then something gets executed. And also here, again, processes must be deterministic, otherwise the whole thing breaks. And a process may generate new events. And now there comes the tricky part. Events will be sorted according to time. So in Kahn process networks, we had no concept of time in that sense. And therefore we need such a list, and the list also has a list management, where we sort these events according to a timestamp. 15, 17, 22, 35. They are always sorted, and if a new event happens, it gets sorted into that list. And each event can contain some input data, and it has an associated process that is sensitive to this event. And the scheduler takes then basically the next event in time and then fast forwards to this point in time. And then looks, okay, at time 15, we have to execute process 1 again with this input data. Well, that's basically how it works. So we have also a scheduler that also triggers these processes. And this is where the concept of super dense time comes into play, the so-called delta delay. And I think it's not doable in 10 minutes, so I think we will do that probably then next week. And if I remember correctly, also next week I have to switch to this slot, but I think Derek will send again a reminder. The exercise will probably not start yet because we have nothing to exercise on yet. So the exercises probably start then the week after. Okay, are there still questions? So I leave this here basically as a cliffhanger for the next week. Still more questions? No, then yeah, thank you for listening, and then see you next week. Yeah.